Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. What is new in the land of science for you this week?
So, quite an interesting story this week. There's lots of people, unfortunately, who've had damage to their spines, or even more deeper, so that their brain is very difficult for their brain to communicate, or they can't control any of their body, and it's basically very difficult for them to communicate. And there have been various people who've been looking into getting information out of people's brains, essentially by putting probes into the brain and reading the signals coming out of the brain, and that's great, but it's kind of invasive. There's risk to it. If you put a probe in the brain, generally you end up getting scarring around the probe, and eventually it stops working as well as it once did. There's a group from Maryland which apparently they've been using EEG signals. These are the signals which you often they're basically the brainwave signals you might have seen on TV. Basically you put attach lots of wires to someone's head, and you measure the voltage all over the head in lots of different places.
Sort of Frankensteinish.
Up till now, people have thought that this is basically because that just sort of measures the sum total of all the neurons in your brain added together. They thought it was far too much mess, too many other things going on in the brain. You'll never get anything useful out of it. But this group in Maryland apparently there have been people who can't communicate any other way, and they've been communicating by just measuring this brain activity and with a word processor, and they can actually control the word processor well enough to sort of write letters one at a time.
That's amazing.
So they can communicate out. They think that they might, once they get it better, they might even be able to start getting movement information. So when they imagine moving their arms, they might be able to get signals out and then maybe control something useful with it. So it's a long way in the head, but it's a very interesting thing to be starting looking into.
Absolutely, very much so. Let's go to our first question. A text this time, Dr. Dave. What would happen if an astronaut spacewalked between Earth and the Moon during a full total eclipse? That comes from Mike on the text. Dave?
Well, I guess during a full total eclipse, basically what that means is that there's some part of the Earth, if you're in the area of total eclipse, and some part of the Earth which is fully in shadow of the Moon, and therefore if the astronaut was immediately between the Moon and the part of the Earth which is in total eclipse, then he would be in shadow as well, so he would see a total eclipse. Of course, if you're close to the Moon, then the Moon would look bigger. So you wouldn't get the really neat thing about total eclipses on Earth at the moment, the recent few tens of millions of years, that the Moon and the Sun are almost the same size, so you can beautifully see the atmosphere of the Sun all the way around it. You see the corona, which I've never seen, because the only total eclipse I've seen, it was cloudy, of course. But yes, so if he was much closer to the Moon, then he would just see big Moon in the way. If he was close to the Earth, then he might see a bit of the atmosphere around the side of the Sun, the corona. I can't think of anything particularly special which would happen other than that, I'm afraid.
Right, let's go to our next question. This time from Dave in Great Yarmouth, sent an email in. Hi Sue, I've noticed on many occasions that the sun's cast sun rays, especially when seen in the distance, photographed or shining partially behind a cloud. How is it we can see the classic sun rays fanning out and always in similar formations? Yes, Clarice Cliff was very inspired by that. Dave, what do you reckon?
Yes, you tend to see these when you've got almost completely cloudy sky with a few gaps in between, so the sun can shine through these gaps. And the thing which many people think is strange about these sun rays is also tends to be when the sun is very, very low to the horizon, sort of in the morning or the evening. And the strange thing is that they look like they're spreading apart, so they all look like they're coming from a single point. But the sun is tens of millions of miles away, so effectively all the light coming from the sun is moving parallel to each other. So why do they look like they're spreading out? And the reason is the same reason why train tracks look like they're spreading apart. Even though the train tracks are always the same distance apart, if you look down them along a straight piece of track, they look like they're close together because they're further away. So although all these sun rays, which are basically sunlight illuminating dust in the atmosphere, are the same distance apart all the way up to the holes in the cloud, they look like they're spreading apart just because of parallax, just because of, as you go further away, things look smaller and closer together.
Now, an email here that's coming from Tad. He says, are fuel injection systems the last word in fuel atomization, or are there any other inventions on the horizons that might make them obsolete and give everyone's cars many more miles per gallon? Apart from solar-powered, I don't know of any, but Dave, you know more than me. What do you say?
I think... Okay, basically in an engine, the reason why fuel injection was a big advantage was because you could control how the fuel was being mixed with the air. You could mix it much more efficiently, and so it would burn much more predictably, and they could design the engine around it and design the injection around the engine, and you get a much more efficient system. As far as I know, most high-tech engines still use fuel injection. Some of them are increasing the pressure behind the fuel injection, so it squirts out much faster. You get smaller droplets, which will burn more completely because you can mix with the oxygen better. They'll burn faster. There's various other neat ways, but that's of making an internal combustion engine more efficient. One of them is actually to use a two-stroke engine. And whilst, the similar sort of normal car engines are four-stroke, you take the fuel, you squirt all the gas, exhaust gases out on one stroke, you then suck in air, you then compress it, and then you squirt some fuel in, you explode it, and that pushes the cylinder all the way out again, and you push all the...
Like a 2CV?
Like a 2CV, yeah. All cars are pretty much all cars are four-stroke, but there's a two-stroke system, which small motorbike engines are, lawnmower engines, which all seem incredibly inefficient and nasty, dirty things. But if you design them right, they can actually be more efficient than a four-stroke. And definitely the very biggest engines, the most efficient engines in the world, are big diesels in things like container ships, which convert about 50% of the energy in the fuel into pushing the ship along. And those are all two-stroke. And I saw a story recently that Lotus is developing a two-stroke engine, which ought to be a lot more efficient. Whether it will ever get to the point of being built, or whether other ways of doing things like batteries and fuel cells will get there before it, I don't know.
There we go, Dr. Dave. He knows, you know. Jennifer has called in, and she drives a lot at night and has noticed in the last year or so a red glow in the sky that is not related to the time. It's usually very late, so it's not the sunset or season or weather. It seems to be all around on the horizon. Any explanation? Oh, could be War of the Worlds, a red glow in the sky. What do you say, Dave?
Red glow? Orange glows I can certainly explain. And you get an awful lot of orange glows from the sky just from all the street lights around the place. If it's all late at night, all night, then it must be somebody putting a lot of red light into the sky somewhere near you. I don't know quite what it would be, not knowing where you live. If you live near an airport, for example, there's a lot of red lights shining up into the sky. You might see them reflected off clouds. Obviously right after sunset or just before sunrise, you'll get a red glow, because the only sunlight which goes through a long way through the sky is red light. Red light penetrates dust a lot better than blue light, so sunsets tend to look red. Other than that, I don't have any immediate ideas without more information, I'm afraid.
Right, now let's go to Dave Bruin, who sent an email in last month, actually. And he was waiting for you because it was a question that he wanted you to answer. He says, Sue, I've got an airband radio. Could you ask Dr. Dave how my radio does pick up aircraft transmissions? Dave, what do you reckon?
Well, I mean, basically, aircraft radios are very similar to any other kind of radio. They basically work by oscillating electrons up and electric current up and down their aerial. That creates radio waves. They get transmitted out. The only difference is how fast the oscillations are up and down the aerial, the frequency of the signal. And so basically your airband radio can tune itself so only to pick up certain frequencies, including the frequencies which aeroplanes transmit at. I think aeroplanes transmit at a couple of different frequencies. There's VHF, which is very close to FM frequencies, which they'll be used for communicating locally. So that only travels probably a couple of 100 kilometres only out to their horizon, depending on how high they are. And they'll use that for communicating with the tower or whatever. But if they're in the middle of the Atlantic, they'll probably use something like shortwave or some much longer wavelength, which will diffract around the corner of the Earth and be able to transmit further than that. Well, of course, if they're in the middle of nowhere these days, they can use satellites as well.
Clever stuff. Our next question comes in by email, and it's come from Rebecca, who's listening in Canberra, Australia. Woo! Hello, all the way across there. I have a Question about combustion space. On Earth, oxygen is required in order for fuel to combust. How does fuel for the space shuttles, etc., combust in space with no oxygen? Do they take extra oxygen and combine it with the fuel? Also, in the movies, you see explosions in space all of the time. And if there is no oxygen, can things really explode?
That is a very good question.
Very good question, absolutely. Dave?
The simple answer is with space rockets, they have to take their own oxygen. You can either do that in a couple of ways. If you've got a rocket based on gunpowder has its oxygen locked up in chemicals. It's in the saltpeter in conventional gunpowder. Then when that burns, it releases more oxygen than it uses up, which will then burn with other parts of the gunpowder and then produce lots and lots of hot gases, which are pushed out the bottom of the rocket, and your firework rocket goes straight up into the air. The space shuttle has a couple of different ways of doing it. The two boosters on the side are basically like giant basically giant firework rockets, and these slightly different chemicals, but the same idea. The tank in the middle and the rocket itself, they have to carry their own oxygen. They use liquid oxygen, and for fuel they use liquid hydrogen. Most of that tank is liquid oxygen because they need a lot more liquid oxygen than hydrogen. And so when they're up in space, it can burn it, and it still works because they've brought their own oxygen. How you see lots of explosions in space. I guess the assumption is there's something with lots of energy in it in the thing which is blown up. So I mean, any space station with people living on it must have its own oxygen there somewhere to keep the people alive. I guess in theory there must be some tanks full of oxygen in case other systems break down. So I guess the tanks react together and burn, which could produce an explosion. Or you don't have to just have a chemical explosion which needs oxygen. You could have a nuclear explosion. They don't need any oxygen at all. And I guess lots of sci-fi films, things are being powered by nuclear power because there's much more power in it, much more energy in the same amount of fuel. So you could have nuclear explosions as well. So yes, things can explode in space, but you won't hear them unless you're very, very close.
OK, before we go to Julie's question, we're going to the phones first of all, because here we have Mike on the line. Hello, Mike.
Good evening, Sue. Good evening, Dr. Dave.
Good evening.
Good evening. What's your question?
Well, I have a question regarding air and astronauts. Now, I don't know if they happen to take all their oxygen supply with them when they go into space, but you've got the likes of the Mir space station. How do they get a constant supply there? Is it supplied to them, I don't know, by the space shuttle or what? I was just curious.
At the moment, they are basically just shipping it up to them continuously. The space shuttle will take some up. Most of it, I think, goes up in Russian supply ships. So they've got small rockets, and then they go up and dock with the space station, and they transfer over oxygen and other useful things for the astronauts up there.
Oh, I guess with their food then, and their water and everything else, I guess.
Yes. They could conceivably at some point in the future start growing plants in space, in which case the plants would absorb carbon dioxide and generate oxygen. But I haven't heard of them doing that on the space station yet. I think it would need quite a big greenhouse to support.
Well, yeah, because I know trees supply a lot of oxygen. That they have to be a big space station to put a lot of trees in there.
Essentially, what you would need is enough plants to produce all the food for the astronauts. Because if you've got enough plants to produce enough food for the astronauts, then all the food which they're eating is that the plants produce the oxygen which it's going to use when the astronauts themselves burn it in their bodies.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, now let's go to Julie's question, Dave, because she asked earlier on the text, when the sun dies, is it going to be a gradual thing over a long time, or will it be a massive explosion? Julie in Bedford, thinking about a suntan.
Depends on what your definition of massive is. I think we've got lots of information of other stars of similar properties to the sun. What we think is going to happen is that eventually the sun will run out of hydrogen to burn. At the moment it's burning hydrogen to produce helium. in nuclear fusion reactions. This is going on very, very slowly, very inefficiently. It's going to take probably about 10 billion years for it to run out of hydrogen. We're about 5 billion years through that. Eventually, the sun's going to run out of hydrogen. It's going to stop producing enough energy. It's going to get colder. That means it's going to start to collapse. As it collapses, it'll get hotter and hotter and hotter until eventually it will start burning helium into carbon. At that point, it will release lots and lots of energy that will push out the outer layers of the sun hugely. It will expand out to somewhere near the Earth's orbit, Earth or Mars orbit. No one's quite exactly sure. And it will turn into a red giant star. Then eventually it will slowly run out of helium as well. And it will start burning carbon to these other things. And eventually there'll probably be a smallish explosion, or it will blow off those outer layers. And it will be left as a very, very small white dwarf star, slowly getting cooler and cooler and cooler over billions and billions of years. But basically, as soon as the sun turns into a red giant, the Earth isn't going to be a very habitable place, and hopefully we'll have worked out a way of getting out of there. But we've got a few billion years yet, so we've got plenty of time.
I hope so, Dave, I hope so. Now, let's go to this question here, which comes from Frances. She would like to know why spiders do not fall off the ceilings or the walls.
There's lots of ways. That most of the ways which insects increase the friction from their feet onto substances on walls and things is by having lots of little tiny hairs on their ends of their feet. Essentially, friction is actually quite a complicated thing. We think it's quite simple on the big scale, but if you look into it, the closer you look into it, the more complicated it gets. One effect is if you get two objects incredibly close together, if you get two just large molecules very, very close together, they tend to stick by a force called the van der Waals force. But you've got to get them to within sort of the size of an atom apart. So one of the reasons why things tend to stick together, if you get them very, very close together, is this force. And therefore, but the problem is, if you put two normal surfaces together, the surfaces are so rough that they only touch in a few tiny, tiny places. So what things like flies and spiders and definitely geckos do is they have lots of little hairs or little hooks, which are kind of slightly flexible, and if they push their feet onto the wall, then they sort of because the hairs are flexible, they can go into all the little nooks and crannies on the surface, and therefore the whole much more area touches the surface, and so it actually sticks quite well. And then they can pull the feet off and they can stick somewhere else, and this force is big enough for them to hang off the ceiling. It's quite impressive with the spider, but the spiders aren't actually very big. If you go somewhere hot, I was visiting South Africa a while ago, and they've got these little lizards called geckos, which are sort of...
I love geckos, they're great.
The actual sort of body is sort of 3 inches long. Yeah, they weigh probably 100 grams, and they run up the walls, up over the ceilings. Sometimes the stickiness doesn't quite work, and you hear a thump in the middle of the night as one falls off and hits your bed. But yes, it's an effect which is perfectly strong enough to hold up a spider and something quite a lot bigger.
All right, let's go to our next question, which is about microwaves. Why do microwaves heat some things and not others? In other words, how do they work? That's from Tony.
Okay, a microwave oven cooks using things called microwaves, which aren't little microwave ovens. They're a form of light. In fact, they're a form of light. Radio waves are another form of light. They're a form of light between radio waves and up the top end of radio waves. So very, very short wave radio waves. Similar sort of frequencies to your mobile phone. But your mobile phone is quite low power, so it doesn't cook you very much. Essentially, this is an electromagnetic wave, and if you put anything in the way of an electromagnetic wave which is charged, so if you put an electron in the way of an electromagnetic wave, it will feel a force, and it will move up and down, which is how an aerial works. The electron feels a force, it goes up and down in the aerial, and then your radio can pick up that signal, and you can listen to us talking now. With a microwave, it essentially depends how good an aerial the thing is which you put in. The frequency is tuned roughly to the frequency which water absorbs quite well. So you can heat up water quite well. It works even better with fat. Fats heat up even more efficiently than water does. But other things which are very insulating, so just a normal piece of china, doesn't heat up at all because there's no electrons to move around. There's just nothing to absorb the energy, so it just sits there and the microwaves go straight through, get absorbed somewhere else. So china's fine as long as there isn't any iron oxide in it, particularly magnetic iron oxide, because you've got lots of magnets in it, there's a hematite in there, and that can turn backwards and forwards, and that can absorb lots of energy, and that can get very, very hot. So that's one of the reasons why some forms of crockery aren't microwave safe, because they get very, very hot very, very quickly. If you put a piece of metal in the microwave, of course, metals absorb radio waves very well. That's what we make aerials out of, so they can get either very, very hot, and also you can get very large voltages at the ends of the bits of metal, and you can get sparks off the end of things. And crisp packets, of course, have a little bit of metal in them. Put a crisp packet in the microwave, you get a little fireworks display.
Doesn't do your microwave a lot of good, does it?
Crisp packets are all right as long as you only leave them in there for about 5 seconds. As long as you turn the microwave off as soon as it stops making interesting sparkling noises. But do ask the person who owns a microwave before you do it.
Absolutely. We'll go round to Dave's house where he'll show you where he's probably recycled quite a lot of things like that. Now then, Dr. Dave, there's one here from Graham in Essex who says, why is it that solar panels are best put on south-facing houses? Surely you should be able to have them anywhere. Dave?
It's quite simple. The sun in this country spends most of its time in the south. It rises in the east. It goes over to the south. In midday, it's always point dead south, and then it sets in the west. And therefore, if you're facing south, then you're going to see more sun than if you face north. If you face north, you're going to spend a lot of your time in shadow. And therefore you're going to get more sunlight. So the best slope to put a roof on, is a solar panel on, is I think sort of something around 45 degrees, 50 degrees, facing south, and you're going to get much more sun on it. Of course, the ideal thing to do is take the solar panel and keep pointing it at the sun all the time, because then it will get the maximum amount of sunlight. That involves a load of motors, and it makes the whole thing more expensive.
Thank you very much. Now then, Mike has said, in all this freezing weather, how come some nice fat buds on plants haven't frozen and split? Because they're very clever, I think, aren't they?
I'm not an expert on plants. I would have thought that various plants, especially plants which live in, have grown up, evolved in environments where there's a lot of frost, will have evolved various ways of stopping themselves freezing. One of the obvious ones is to use some kind of antifreeze. Basically, if you dissolve lots of things in water, then you can reduce its melting point. Salt works fine, which is why they throw it out on the roads during the winter. Sugar will work as well. It's just more expensive than salt, so they don't use it on the roads. And so if they've got lots of sugars in the cells in the plant, then things aren't going to freeze. I know various sort of fish in Antarctica have developed proteins, which means that they can freeze, and it doesn't do them much harm.
Wow.
Because normally the problem is that all the cells in an animal or plant are bags of water, and ice crystals are pointy, and they kind of break holes in those bags of water and split them. And as soon as a cell is broken, then it's dead. There's no way it's going to work. It's an incredibly complicated chemical machine, and if you mix it up with other cells, then they just die. And so they have ways of making the ends of the ice crystal less pointy. Of course, the other thing that a bud could do is generate heat. It could burn sugar in order to keep itself warm, and possibly even have an insulating layer around the outside of the bud. So I don't know which of those are used. My guess is nature's probably used all of them in different places.
Clever stuff. Mother Nature. All right, well, Mark is asking, has the recent earthquake knocked the Earth slightly off its axis, as some folk have said, losing us some microseconds? Ooh, what do you think about that, Dave?
I've heard this story in various places. There's an American scientist who has a model who has looked at how the rocks have moved in this earthquake, and he thinks it will have slightly changed the Earth's, the period of the Earth's orbit, the speed of its rotation. The reason why it would do is that if you've ever played on a roundabout in a playground, once you've got it spinning, if you move towards the middle, then you'll speed up. If you move to the outside of the roundabout, you'll slow down. And therefore, if the earthquake has on average moved mass, a load of rock, upwards, then you'll slow down the Earth's rotation. If it moves it inwards towards the centre, then it will speed it up. the effect is probably much smaller than lots of other things which are doing that all the time. So all sorts of other plate tectonics, moving mass around, will slightly change the speed of the Earth's rotation, as will erosion and lots of other things. So if it has, I'd be very surprised if we could notice.
Now, Leslie's called in and says that helium-3, I don't know what that is, but it can be very easily mined on the moon, and one shuttle load could power the US for a year. Is this true? And if so, why is it not being followed up? Yes, Dave, why?
Helium-3 is a type of element helium. Helium is the stuff which you fill balloons with, which float.
Makes your voice go funny.
Makes your voice go funny. Helium-4 is the normal helium, which you find, in fact, they tend to find it in the tops of certain American oil wells. There's quite a limited amount of it on the Earth. Helium-3 is basically a quarter lighter than helium-4. Helium-4's got 2 protons and 2 neutrons in it. Helium-3's just got 2 protons and 1 neutron. It would be really useful because if we could build a nuclear fusion power station, it would work a lot better than the other fuel, which is tritium, which is 1 proton and 2 neutrons, because the energy coming out of helium-3 would be thrown out by shooting out a very fast proton, which is charged, and we can control that using magnetic fields, and we can absorb the energy out of it much more very efficiently. But when you do nuclear fusion on tritium, then you get all the energy out in neutrons, which aren't stopped by anything. They're actually a very lethal form of radiation, and they'll go through most of your machine, which your nuclear power station. They'll make things radioactive. They'll damage the metals you've used to make it out of. So if we can burn helium-3, that would be a lot better. There is some of it on the moon, and a shuttle load I could quite believe, could power the US for a year. The problem is getting that shuttle load of helium-3. Although there is some on the moon, there's not very much. You've got to process 100 million tonnes of rock to get 1 tonne of helium-3 out. Shuttle load is maybe 10 tonnes, so you've got to process 1 billion tonnes of rock, and you've got to get the machines to the moon in order to dig through all that rock and dust. You've got to heat it up to get the helium-3 out. It's not going to be an easy or a cheap option, even if we did get the nuclear fusion system working on Earth, which we haven't done yet. So it is something, it's not being hidden, it's just very, very difficult and possibly not economic. I'd be surprised if it was cheaper than building solar cells, which is the other option. Use nuclear fusion in the sun, which is producing lots of energy all the time. Lovely nuclear fusion reactor built there already for us.
There you go. I hope that's answered your question, Les. All right. Dom has asked, how does the whitening in toothpaste keep your teeth white? And an interesting one here, a bit of fun from... where's it gone now? Oh, yes, from the Wasp, who says, if Dr. Dave had a time machine, where would he like to go back to?
I'll start off with the whitening toothpaste quickly. There's a couple of ways of whitening teeth. One of them, which only dentists do, is essentially to use a very weak abrasive and basically rub off the surface of the enamel on your teeth, which kind of rubs away any stained enamel. The problem with this, if you do it too often, then you wear away all the enamel and you don't have any of the lovely hard enamel on the outside of your teeth, which keeps them nice and strong and protects them, and your teeth disintegrate. Lovely teeth, Sue.
Thank you.
And the other way which they do in toothpastes is add something which essentially acts like a bleach. And in fact, they use hydrogen peroxide, which is the stuff you use to bleach hair. They put that in low concentrations in the toothpaste, and that will oxidise things. Preferentially, it will oxidise coloured things, because coloured things happen to be more easily oxidised than other things, and they tend to cease being coloured with any luck, and so it basically just bleaches your teeth, and they look whiter. Time machines...
To a building?
I don't know about a building. Something I've always think would be interesting. I'm not sure I'd actually like to do it, but is it very interesting to think about? I've always wondered if you were put a long way back in time, how much effect you could have on technology, and whether you could build a useful technological civilization by what you know.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.